We're now ready to understand why we call these weird functions we've been working with hyperbolic trig functions. We've seen a number of connections with trig, okay? Haven't seen anything yet with hyperbolas, and we've seen a lot of differences with the trig functions as well. If we look at regular trig, I know that the unit circle definitions of my sine and my cosine are that if I draw an angle in standard position, the point where it intersects the unit circle has an x and a y value. And that x value is going to be cosine of the angle. Here I've just chosen to call the angle t. And the y value is sine of that angle. Okay. Now the equation for the unit circle is x squared plus y squared equals 1. If x is cosine of t, x squared becomes cosine squared t. If y is sine of t, y squared becomes sine squared t. So that's my basic Pythagorean identity for regular trig. It really comes from just the equation of the unit circle. We say here that sine and cosine parametrize the unit circle. When you have a curve, and you parametrize it, you're describing points on that curve, both the x and the y value, in terms of a single variable, in this case t, which we call our parameter. Okay, well, this is the unit circle. What I've drawn over here is the unit hyperbola. The equation of the unit hyperbola is x squared minus y squared equals 1. So similar to the unit circle, except that it's a subtraction problem instead of addition. Okay. Now, I've marked off on the right-hand side that I could associate a point here as the x value being cosh of some number t, and the y value being sinh of that. Now, I did not draw that on the left-hand side, because I know that cosh is never negative. So there's no way that cosh could describe the x value of a point on the left half of the unit hyperbola. But if I restrict myself to the right half, notice that x squared, or x being cosh t, x squared becomes cosh squared t. Y being sinh t, y squared becomes sinh squared t. Cosh squared minus sinh squared equals 1. That's the identity that we just proved. So this says that cosh and sinh parametrize the right half of the unit hyperbola in the same way that cosine and sine parametrize the unit circle. Pretty cool. Now, you'll work with parametric curves when you're in 3b, and then a whole lot more when you're in 3c. But the beauty of this is that a curve is essentially a one-dimensional object. But if this curve lives in 2-space, then to describe a point on that curve, I need two variables. I need the x value and the y value. When we parametrize it, we describe both of those in terms of just a single variable. So parametrizing something is a way of matching the number of variables that you use to describe it to the dimension of the shape itself, as opposed to the dimension of the space it lives in. That becomes really important in 3C. Not super important now. This is just sort of interesting trivia. Now, with the unit circle, I can think of t as being my angle. That doesn't work so well here, but there is a connection. I've shaded this area here. Now, I've shaded the area that we would have if t was a positive acute angle. But if I calculated that area of a sector, it turns out that that area is just t over 2. And I can continue that if I think of it as signed area, so that if my angle were negative and I was rotating clockwise, I would count the area as negative. And if I allow for angles that are bigger than 2 pi or more negative than negative 2 pi, that I can count some area twice. So that if I were to go around the unit circle 1¼ times, I would say the area that was swept out was the area of one full circle, which would be pi, plus another quarter. So we get a total of 5 pi over 4 as the area when my angle was 5 pi over 2. Okay, excellent. So here, I've also shaded some area. Okay, I just drew in a diagonal line segment from the origin to the point on the hyperbola, and it turns out that that area is t over 2. And if I use the convention that I count area down here as negative, sort of the same as I would count signed area as negative if I were rotating in the negative direction, then that signed area does always correspond to t over 2. Now, I'm not expecting you to have that trivia fact memorized, but I did want you to see that there was a method to the madness. There is a very good reason that we do in fact call these hyperbolic trig functions. And the name comes from the fact that just as regular cosine and sine parametrize the unit circle, hyperbolic cosine and sine parametrize the right half of the unit hyperbola.